In the previous session, we had seen what a beta function is. We had derived this integral and we had seen the relation between the beta function and the gamma function. Beta function is symmetric. That is, b of m comma n is equal to b of n comma m. So let's prove that. By definition, we know b of mn is equal to the integral from 0 to 1 of x to the power of m minus 1 times 1 minus x to the power of n minus 1 dx. Now we do the substitution. Y is equal to 1 minus x. Differentiating it, we get dy by dx is equal to minus 1, which implies dy is equal to minus dx. Y is equal to 1 minus x means y minus 1 is equal to minus x, which implies x is equal to 1 minus y. Taking care of the changing of limits, when x equal to 0, y is equal to 1. And when x equal to 1, y is equal to 0. Now carrying out the substitution, we get beta of m comma n is equal to the integral 1 to 0, because the limits have got interchanged. 1 to 0 of x to the power of m minus 1. That is, x is 1 minus y. So 1 minus y to the power of m minus 1 times 1 minus y to the power of n minus 1. And dx is minus dy. Simplifying it, we get beta of m comma n is equal to minus the integral 1 to 0 of 1 minus y to the power of m minus 1. 1 cancel out. We have y to the power of n minus 1 dy. Now, to make this minus sign disappear, we exchange the limits again. So, integral 0 to 1 of 1 minus y to the power of m minus 1 times y to the power of n minus 1 dy. So here, if you look at this expression and this expression, the only difference is the variable of integration. Here it is x, here it is y. But we know that the variable of integration doesn't matter in case of definite integrals. So these two integrals are the same, since x and y are dummy variables. So we have arrived at the fact that beta of m comma n is equal to beta of n comma m. That is, it is symmetric. Make sure that you observe that it is actually symmetric. Here we have x to the power of m minus 1. And here we have x to the power of n minus 1 times 1 minus x to the power of n minus 1. Here we have 1 minus x to the power of m minus 1. So we have this symmetric nature of beta function. So that was one interesting point. Now the claim is that beta of m comma n is equal to the integral 0 to infinity of y to the power of n minus 1 by 1 plus y to the power of n plus m dy. So here, if you notice, the limits in case of beta function is 0 to 1. Here we have the limits as 0 to infinity. And the claim is that they both are equal. So let's see how we can see whether that is true or not. So again, we start with the definition. Beta of m comma n is equal to the integral 0 to 1 of x to the power of m minus 1 times 1 minus x to the power of n minus 1 dx. Now we carry out the substitution. X is equal to 1 by 1 plus y. And differentiating it, we get dx is equal to minus 1 by 1 plus y square dy. This x equal to 1 by 1 plus y can be written as 1 plus y is equal to 1 by x, which implies y is equal to 1 by x minus 1, which implies y is equal to 1 minus x by x. Now, taking care of the change of limits, we get when x equal to 0, y goes to infinity. And when x equal to infinity, y goes to 0. So now carrying out the substitution, beta of m comma n is equal to the integral from infinity to 0. So here the limits have got interchanged of, here we have x to the power of m minus 1 and x is 1 by 1 plus y to the power of m minus 1 times 1 minus x. So 1 minus x is again 1 by 1 plus y to the power of n minus 1 times dx. So dx is minus 1 by 1 plus y square dy. Again, we have to be very careful with substitutions. Now, beta of m comma n is equal to the integral from, you see this minus sign? We can get rid of this by changing the limits because we know anyhow it will come out of the integral. So integral from 0 to infinity of 1 by 1 plus y to the power of m minus 1 times 1 plus y minus 1 by 1 plus y to the power of n minus 1 times 1 by 1 plus y square dy. So we have beta of m comma n is equal to the integral from 0 to infinity of, this remains same, and here 1 and 1 cancel out. We have y by 1 plus y to the power of n minus 1 times 1 by 1 plus y square dy. Here 1 to the power of m minus 1 is 1. Here it is 1. And here we can split it, the exponent. Y to the power of n minus 1 by 1 plus y to the power of n minus 1. So now we can combine. So we have y to the power of n minus 1 divided by 1 plus y to the power of m minus 1 plus n minus 1 plus 2. Simplifying it, we get beta of m comma n is equal to the integral 0 to infinity of y to the power of n minus 1 by 1 plus y to the power of m plus n minus 1 plus 2 is 0 dy. And this is exactly what we had to show. So that's another interesting identity, we can say. One more proposition. Beta of m comma n is equal to 2 times the integral 0 to pi by 2 of sine to the power of 2m minus 1 theta times cos to the power of 2n minus 1 theta d theta. Again, you notice that here it is 0 to 1 and here it is 0 to pi by 2. So let's see. Again, starting with the definition, beta of m comma n is equal to the integral 0 to 1 of x to the power of m minus 1 times 1 minus x to the power of n minus 1 dx. And differentiating it with, we get dx is equal to 2 sine theta cos theta d theta. Taking care of the change of limits, when x equal to 0, sine square theta equal to 0, that means sine theta is equal to 0, that means theta is 0. When x equal to 1, we have sine square theta equal to 1, that means sine theta equal to 1, that means theta is equal to pi by 2. So now carrying out the substitution, we get beta of m comma n is equal to the integral from 0 to pi by 2 of, we have x. So sine square theta to the power of m minus 1 times 1 minus sine square theta to the power of n minus 1 times 2 sine theta cos theta d theta. Okay, simplifying this, we get integral from 0 to pi by 2 of sine to the power of 2m minus 2 theta times 1 minus sine square theta is cos square theta. So cos to the power of 2n minus 2 theta times 2 sine theta cos theta d theta. Okay, now bringing in the sine theta, combining these like terms, we get integral from 0 to pi by 2 of sine to the power of 2m minus 2 plus 1, that is 2m minus 1 theta, times cos to the power of 2n minus 2 plus 1, that is 2n minus 1 theta, times d theta, and 2 goes out of the integral. So finally we have shown that beta of m comma n is equal to 2 times this integral. All very interesting. So if you found this useful, don't forget to like, share and subscribe. Questions, suggestions and comments are always welcome. Thanks for watching. See you in the next session. That's it for now.